Hello, this is Hakyeong from KAIST. This is a collaborative work with Andreas Meuleman, Daniel S. Jeon, and Min H. Kim. I am going to present our work entitled High Quality Stereo Image Restoration from Double Refraction. Double refraction is an optical phenomenon that occurs when light passes through a birefringent medium. An incident ray splits into two rays depending on the polarization property. One is called an ordinary ray, which propagates along the plane of incidence, and the other one is called an extraordinary ray, which propagates along the Walker plane. Due to the different direction of the light path, disparity occurs between the array and array, which results in a superimposed stereo image made of two different rays from disparity. We developed a method that allows us to restore two stereo images from a monocular double refraction image so that the restored stereo images could be later used for the several applications such as stereo imaging with a single camera. One of the challenges in stereo image restoration is that these two superimposed images in double refractions are different from each other depending on depths. A perfectly accurate depth-dependent deconvolution kernel per pixel is required in advance for restoring stereo images. In this work, we restore stereo images without estimating depths from the superimposed images. Previous work exploits birefractive stereo for RGBD imaging. This method estimates stereo depth maps and color images, but they focus on the restoring clean array image only. When both array and array images are restored by the previous methods, the restored array images often present blurriness due to the preceding inaccurate depth estimates, and the restored array images are not clearly separated from the input double refraction images. To restore the stereo images without depth information, we formulated an image restoration problem from an uneven double refraction image. Placing a linear polarizer in front of the calcite medium attenuates array and array with a different ratio. In our methods, the input double refraction image is the superimposed sum of the weighted array and array images. Based on our image formulation model, we first create a synthetic rendering datasets of the double refraction using existing RGBD dataset. According to our image formulation model, the difference between the double refraction signal and each array and arrays include a common term G. With our training dataset, we trained our network to learn how to estimate the common term with the convolutional network and also induce the inverse sign of the term with two different global skip connections. Our network architecture consists of one backbone network stacked with the residual blocks, and two head networks consist of the transposed convolution. One skip connection adds an output estimation to the input element wisely, and the other skip connection subtracts the output estimation from the input image element wisely. Here are our synthetic restoration results on the test dataset. From the input double refraction input images, we restore both array and array with high accuracy. The quantitative evaluation with PSNR and SSIM metric also validates that our method quantitatively outperforms the existing birefractive stereo method. Here are our restoration results of real scenes captured by our prototype camera. Our restoration network also successfully restores the stereo image robustly from the real scene. Here we demonstrate an application of our method that estimates the depth information from the estimated stereo images of the synthetic and real scenes. In conclusion, we present a novel stereo restoration network that can restore stereo array and array images with high accuracy without relying on depth. It enables the capturing high-quality stereo images from the single monocular camera input.